All right, guys, so we're going to talk today about defining different types of systems and differentiating between open, closed, and isolated systems through analysis, application of conservation of matter, and conservation of energy. Again, it's going to make more sense whenever we actually look at it and when we start applying it to our stuff. This is our first set of notes for playlist 2 of this unit. So a system. Whenever we talk about systems in physics, we're going to be talking about just whatever object or objects that we have chosen to be analyzed. So whenever you read a question, oftentimes you'll have to figure out what you need to focus on in order to answer the question that's being asked. Sometimes they tell you what the system is. You guys had a test last semester where you had to draw a free body diagram for a block on a ramp, but then it said to draw what it would look like if it was the block ramp earth system or something like that. And so sometimes it's defined in the question, and then you have to take a closer look at which of the forces are external to my system, which ones can I still draw acting on the system. But it's whatever object or objects you're focused on, and that could be something that's defined for you in the question, or it could be something that you are defining based on what you have determined you need to solve for, what is the best path to get there. We have two types of systems, and we talked about these in our dynamics unit when we talked about forces. We talked about no internal structure and rigid body, and I kind of gave you definitions then, but we're going to remind you what those mean. But we're going to focus on no internal structure systems. Again, same thing as we did before for this unit. As a reminder, a no internal structure system is one in which the makeup of the system is ignored and we focus only on external interactions. So we ignore the system's internal energy, and the way that the system is set up doesn't really matter. Okay, so sorry, I'm going to go back real quick because some of you might be writing. But we're going to just focus on forces external to that system and how they affect the system, but the makeup and the arrangement of the objects don't really matter in this. On our free body diagrams that we drew previously for no internal structure systems, we just drew center of mass, a point, and we drew all of our forces acting on that point, or originating from that point. Okay, and it's going to be the same idea here. The other type of system that you can set up is a rigid body. And whenever we do that, the internal structure of that system will matter, and the internal interactions therefore must be analyzed. Now, we're not going to be dealing with rigid body systems yet, but they are going to be important later on whenever we look at, like the last point there, the configuration of the system, or actually it's not on this one, it's the third one. We'll see this when we analyze simple pendulums and mass spring systems where we do care about interactions within that system. And you have to consider those internal forces or energy. But the configuration of that system will lead to analyzing that internal energy. And again, it'll make more sense whenever you see some examples of it. But for now, you're just writing down definitions. You're also going to use those rigid body systems when we get to rotation later on as well. Okay, so which type do you use? Unless it is specified in the question, you get to choose how to define the system. Okay, so you're going to pick whichever is easiest for you in order to analyze whatever scenario or problem that you're given. So again, sometimes it is specified, in which case you obviously need to go with that, but if it's not, choose whichever one's easier. Okay, and so you have to start thinking about those interactions and what would make your life easier, how you could solve that problem easier. Do you ask yourself questions like, do you need to consider interactions within the system itself, between the system and its surroundings, or both of those things? Okay, and that will help you to determine which type of system that you need to use for that scenario. It's going to take a little bit of practice to get the hang of it. Okay, there are also different ways that you can set up your system based on interactions you need to consider. Okay, and so we're going to talk about open systems, closed systems, and isolated systems, and what the difference is between them and when you use which type of system. And again, it's going to depend on what you're trying to solve for. So it's dependent upon the problem that you're answering. But we have 3 types. We're going to go over each of them. So again, you can jot down notes on each, starting with an open system. Okay, so an open system is where you have a system that is able to exchange conserved quantities with its surroundings. This could be energy, matter, or anything that we know should be held constant. You guys have heard of things like law of conservation of mass, law of conservation of energy. Okay, things that you know should be held constant. If you have an open system, they aren't necessarily held constant because that system can exchange with its surroundings. And that's what it says on the second point. In an open system, however, these wouldn't be constant because they would be able to leave or enter the open system. So again, in an open system, the system is able to exchange those conserved quantities with its surroundings, meaning you can have an exchange of energy with your surroundings, you can have an exchange of matter with your surroundings. Those are the two we're really going to focus on. Okay, so here is an example of an open system. Assume you have a cup of coffee in a mug that you wish to analyze the coffee mug system. We could consider this to be an open system where we could add sugar and creamer to our coffee, and of course in that case it would be open because we just added matter to it. Okay, so we no longer have conservation of mass. Okay, or we don't necessarily have conservation of energy if heat is able to leave our mug and warm up the air around it. Okay, but again, simple example, but same idea. Whenever you're looking at different scenarios, what you're trying to solve for, you're going to define it accordingly. Of course, in that example, matter is no longer conserved within the system, and based on what I've written, and not necessarily energy either if we're dealing with something where it's radiating heat to its surroundings. Okay, the second type of system is a closed system, and that is going to be a system where you can exchange energy with the surroundings, but you're conserving all other conserved quantities. So we're not going to have matter entering or leaving our system. We are going to have conservation of mass, but this is a scenario where you could have energy that is dissipated from your system, but the matter must be conserved. Okay, so that's the difference between open and closed, is that in a closed system, the matter must be conserved, but the energy can exchange with the surroundings. So again, we'll look at the same example with a coffee cup, and I kind of mentioned this a minute ago. With our open cup, before we could have matter exchange or heat exchange. But with the closed system, let's say that we now put a lid on it. So now we can't add anything to it. And so in our new coffee mug lid system, we're not going to have any mass or any matter leaving or entering the system, but we could still have thermal energy. We could have heat. That's what it says. It could be a closed system because energy could leave the system. Your hand could get warm, thermal energy, but you can't add or remove matter if the lid is on the cup, I guess, unless you took the lid off. Okay, but in that closed system example. The last one is an isolated system, and I know we're using simplified analogies here with our coffee cup, but again, you can look at it as it applies to different physics scenarios in your task options and checkpoint. But an isolated system is going to be a system where all of those quantities are conserved. It conserves all conserved quantities. So there's going to be conservation of energy, there's going to be conservation of matter. And so you're not going to have a transfer of either of these. This is going to be more of like an ideal situation, not necessarily super realistic real world, but oftentimes we need to focus on the question at hand with an ideal scenario like that in order to answer it. Again, it depends on what you're being asked for. Okay, and so you might want to define your system as an isolated system where all of your energy is conserved and all of your matter is conserved. Again, example, back to our coffee cup. Let's assume now that this is a perfectly insulated mug. So now we have the same coffee mug lid system, but it's perfectly insulated and it cannot exchange heat with its surroundings, and that would make it an isolated system where all of that thermal energy is kept inside of our system. Nothing can be added or removed. That makes it isolated. All right, so let's see if we can look at some example scenarios and how we could define our system in some of these scenarios. Okay, more physics related than a coffee cup. So here we have a ball is thrown upwards to reach its maximum height, and the question that I'm asking you is how far is the maximum height from the point of release? Okay, we're just going to focus on how we could define our system in order to answer this type of question, because obviously I haven't given you enough information in terms of numbers. You don't have any numbers. Okay, but since we want to know about the ball's position change, we could set the system as just the ball. We could say, okay, my system is this ball. Okay, and if my system is a ball, we could determine if we're dealing with an open, closed, or isolated system. And in order to answer that question, you need to ask yourself two things. Does it gain or lose matter? And does it gain or lose energy? Because that's the two criteria that differentiate between our different types of systems. So thinking about this example of this ball that's been thrown upward, does it gain or lose matter? Let's start there. No. Okay, we won't have any gain or loss of matter. What about energy?
Yes.
If it's just the ball, yes. Okay, we could have a gain or loss of energy. It will slow down, for example, as it rises. And so it will lose kinetic energy. So, of course, it will have a change in energy, which means energy can be exchanged with its surroundings, which makes it a closed system. Okay, because we can't exchange matter, but we can exchange energy in that example. All right, so let's look at the same scenario, but what if we considered the ball-earth system instead? Okay, so we had just the ball a second ago, but what if it's the ball-earth system? Okay, and the force of gravity was external for the ball system. When it was just the ball, gravity was an external force acting on that ball that caused it to slow down as it rose. That's why it lost kinetic energy as it rose. Okay, but if we make our system the ball-earth system, it's now an internal force. And when we look at it as an internal force, okay, we don't want to consider that when we're looking at the energy changes there. Okay, the same way that we didn't consider them when we drew our free body diagrams previously. Okay, are there any other forces acting on the ball-earth system? Nope, nothing else. The only thing that we're going to consider is that internal force, okay? So now we don't have an external force acting on our system, which means if there is no external force acting on our system, we're going to have conservation of energy. We're not going to have that change in energy if we define it this way, okay? And that makes it an isolated system, because instead of saying that the Earth's gravitational field is doing work on the ball to cause it to lose kinetic energy, now we're going to say that our kinetic energy is being converted into gravitational potential energy. I know we haven't talked about all these terms yet, but the way we define it is different. Okay, and we're going to do it in terms of a different variable, but this makes it an isolated system. Okay, so if you have no external forces acting on your system, you're going to have conservation of energy, you're going to have an isolated system. And sometimes you need to define it that way, and other times you need to define it the other way. Depends on what information you're given. All right, here's a second question to consider in this exact same scenario. We still have this ball being thrown upward to reach its max height, but now I'm going to ask you, how much force did the hand apply to the ball? In order to throw it up in the air in the first place, how much force did the hand apply? And again, you need to think and ask yourself questions like this. How can I define my system to find the force that was applied to the ball? Okay, if you want to consider that question, we could say based on the acceleration, we could find the force applied, so we could just analyze the ball. Okay, and if I want to figure out how much force the hand applies to the ball, I could make my system the ball, and I could look at the acceleration of the ball due to the interaction with the hand, and I could find my answer that way. Okay, again, considering my system as just the ball, does it gain or lose matter in this scenario? Again, you're going to ask yourself the same two questions. Does it gain or lose energy in this scenario, so that we can figure out what type of system we have? So matter, our answer is almost always going to be no to that one. Okay, but what about energy? Does the ball gain or lose energy whenever you throw it? Yes. Okay, throwing it's going to, of course, cause it to gain energy. And we have this external force on our system. The hand is external to my ball system. And so we are going to have a closed system in that example. Questions about this so far? Okay. Again, what if we analyze it as the ball-earth system? So instead of just the ball, now we have ball-earth. What type of system is that? The hand is still external to that system. If your system is the ball-earth system and not the ball-earth hand system, you still have an external force, which means it causes a change in the system's energy, so it's still a closed system. right, guys, so I told you it'll make more sense maybe when we put some numbers with it, but those were some physics examples to consider. Hopefully that clarified it a little bit. If not, then please make sure you ask questions. But today you can use the rest of your class time to work on playlist 1, which is due today. Alternatively, if you've already finished that, you can get started on playlist 2, although we do have some more notes in playlist 2, but you can see how much of it you're able to answer. So take a look at those task options and checkpoint, and if you have questions, please let me know.